Hello everyone, my name is Paul Yu. I'm a member of the Material Science and Engineering Department at the National Taiwan University of Science and Technology. Today I will present the paper Label-Free Organic Electrochemical Transistor Source Active Hybrid Biosensor based on gold nanoparticle decorated PETA films. As a brief outline, my presentation is divided into three parts: introduction, result discussion, and calculation. In the introduction, I will mention the importance of neurological and chronic kidney disease and our device. As a background information, our lab has continually conducted research on the morphology of micro-nanostructure PETA technology, including micropattern, micro-rod array, neural array, 3D scaffold, aligned nanoparticle, and hierarchical nanostructure, making it possible to form structure from 0 to 3 dimensions of the PETA, which we apply as hierarchical nanostructure to the OECD source device for detection of DA and PC. First, dopamine is a neurotransmitter that plays important physiological roles. Dopamine-related neurons is associated with Parkinson's. Moreover, determining the levels of DA in biological system can provide valuable information for the diagnosis and treatment. Second, we consider precursor, which can be excreted by the kidneys. Therefore, the detection of serum PC can influence disease treatment and prevention. PETA-PSS-based organic electrochemical transistors have recently for the high electrochemical identification capability, easy operation, low cost, and stable performance. In addition, source active substrates have been used for their big potential to detect complex biomaterial due to their high chemical identification capability, high sensitivity, low cost, and less time-consuming operation. This paper is the first to demonstrate OECD source hybrid biosensors for the efficient detection of DA using OECD with the additional capability of sensing PC using source spectroscopy. This is result and discussion. Gold nanoparticles are particularly attractive nanomaterial for electrochemical bioscience because of their efficient signal amplification, good stability, and outstanding biocompatibility in electrolyte solution. The picture that you can see now the different layers of our device. In picture A, we show the oxidized polymerization process of the PSH film. In the picture B, we have the structure of PETA. In picture C, we have the full procedure. At first, we spin coating PETA on the bottom layer and then coating PETA-SH on the upper layer. E and F shows the schematic representation of OECD source hybrid biosensor for DA and PC detection. This procedure was made with the help of Alchemia Silicon. Now, look at the left picture. Here we can see that the oxidized polymerization process of the PSH film led to ready formation of 3D porous-like nanostructure. In the upper right picture, we can see the UV visible absorption spectrum and the photograph of the aqueous solution of citrate-capped gold nanoparticle. The lower right picture E, we can see SEM image of treated citrate AuMPS of PSH. This picture indicates that P has better conductivity than PSH and AuMPS treatment on lower right. Because the gold nanoparticles on the surface have more citrate, the data potential of AuMPS treatment can get a negative 70 point for MV. In the lower right, we can see the formula for that potential that uses different walls that we process. Now, we first must say that the area enveloped by the sweep of the CV curves decrease from P to PPSH. In picture D, we can see the impedance increase from PSH, AuMPS to PSH and to P. Next, we have the DPV is differential pulse voltage curves of various PDA films in PPS containing AA, DA, and UA with various concentration. A and D for P, B and C express PS, E and F express AU and PS PSH. After testing in both high and low concentration on each of the previous device, it could be seen that the A1PS PSH present the best sensitivity even at a lower concentration. In order to understand our OEC device better, the on-off ratio was tested. This is on-off ratio decreased from AuMPS PPSH to PPSH, suggesting that the high specific area of AuMPS coating may have enhanced the electrical conductivity of PPSH. While the 200 nanometer thickness of P underlying layer display the best OCD performance and could possibly be used for DA detection and was closer zero voltage on its properties, which is better for ideal OCD properties. Figure displays the transconductance response of AU1 PPSH OCT measured at various DA concentration in PPS in the presence of A and UA. We know from a previous DBV experiment that we have a very small interference from A and UA because A1PS are negatively charged and have specifically that can exclude UA and A. Both of them have good sensitivity at low concentration of DA. In addition, DBV detection showed no interference in electrochemical detection with PCIS and UA. The Lyman shift of styrene in PDA is 1500 cm. In lower left, we can see higher PC signal in Raman shift. The A1P PPSH device provides a higher intensity Raman signal for PC due to its greater source activity in the presence of DA, UA, and AA compared to PPSH device. Because the AU particles have electric field to enhance Raman signal, the source intensity of the band at 906 cm was enhanced. Additionally, PC concentration have more sensitivity at the lower concentration compared to higher concentration in which the hotspot effect decreased dramatically. A1PS PPSH device was capable of detection PC over a wide concentration range with high specificity when using a ternary aqueous solution of DAUA and AA. Well, let's make a summary. This novel OECD search hybrid biosensor band features a highly cognitive PDA-PSH film. We have developed a PDA-based 3D OECD device decorated with a high density of AuMPS for the effective detection of DA in the presence of multiple interference, and a source-active substrate for the selective detection of PC on the same chip. The PDA-based OECT search hybrid biosensor decorated with high density of A1PS display new versatility for electrochemical and source enhancement, encourage the design of next generation biosensor for point of care diagnostic. Thank, thank you everyone for listening. This is the end of my report.